We're going to look at a very fascinating example to me. I find this very, very interesting. And this is maybe, again, I mean, statistics has a lot of real-world examples, but I have to admit this one's really cool. And not least of which because sometimes I'm asked to do this kind of stuff. We're still hypothesis testing, null versus alternative hypothesis. And we've done a lot of examples that I think maybe were medical related. We talked about my cat with breathing. We talked about life expectancy in Texas. We're going to come back to life expectancy in maybe the next section from this one. But as is usual, you want to organize statistics in your mind. And we've talked a lot about how we have the technical things that we do, and you also have sort of the philosophy of picking which of the many tests you can do. And I realize that maybe a Rolodex is a very, very arcane object nowadays, but a Rolodex was a little spinner and it would have a whole bunch of people's names on it. You could spin through your Rolodex and pick out the address you want. Maybe think of an iPhone's address book now. And the address book is, I think, very much like your mind. If you get technical proficiency in dozens or maybe hundreds or thousands of tests, then your mind suddenly has a lot of ideas about what it could do, and you have to become very good at deciding what of those many things to do. Should I pick these two or should I pick those two? Does this one even work? That's part of the question. So being very good at being able to sort, when you look at a problem, which of these many tests should I do? And then being able to actually do the tests that you know you should do. Those are kind of two separate things, but they're very much linked. So to help understand which test to pick, remember and think back to Module 7. We talked about confidence intervals then, and we had discussed very much how we started off knowing a lot of information. We had some information about the sample data, but we also knew things at the parametric level. We knew sigma. And then we said, well, what if we knew a little bit less? What if we only knew sample data and maybe only knew mu or so of the population level? And then we said, what if we don't even really have a list of data? What if we just have some yes or no possibilities? And that would be binomial distribution. And when I organize things in my mind, I think that for either z-scores or t-scores, I tend to have a long list of data, and I can calculate things off those data. Whereas in the binomial distribution process, sometimes I have only limited data. We have a very specific question we're answering, a yes or a no separation, and so then we only know maybe how many people we talked to and how many times we were successful. And we talked about some presidential approval ratings with that. So now fast forward to Module 8, we're still talking about hypothesis testing, and we've already talked about hypothesis testing when we know a great deal about the scenario we're in. We knew information about all the CAT standard deviations because that had been well studied. And then we talked about a scenario where we did t-scores where maybe we knew a little less. I only happened to know the population average and I didn't find quickly what the deviation was for that. So now we're going to continue talking about hypothesis testing. Left, right, and two-tailed continues to mean the same thing it always does, and as natural, it's time to talk about binomial distribution. And now that we've seen binomial distribution in Module 5, Module 6, and Module 7, and now Module 8, you're starting to get a little bit more familiar with it. So you're completely unsurprised when I tell you that the number of successes and the number of failures has to be bigger than 5. That's required for us to use the normal distribution in place of binomial. I just said the magic word normal distribution, so you know that we're talking about a z-score again. Despite maybe the less technical nature of our data, because it's a binomial scenario, we actually have quite a bit more going on for us, and so we can get out of the messy t-distribution and get back to some honest z-scores, get back to normal. Of course, q is 1 minus p, and our good estimator, our point estimator for p, is going to be p hat, the number of successes divided by the number of total attempts. So now, having said that, you know what 5 steps we're going to try. Let's apply this framework to tackle a new kind of problem, and this is the problem I'm really excited about. This problem uses what we call Benford's law. Benford's law is interesting. Several people had noticed this back in the day. Now we have a table in our book too, and maybe you don't get to use your table often enough because now we've got technology. But back in the day it was very hard to print new books. So, and new tables. So there would be a table, and maybe one school might share a table all amongst all of them. And so some people started noticing, I think an astronomer and then Benford then later on, noticed that the early parts of a table are used more than the later parts. And the early parts are those ones that tend to have 1 as the first non-zero leading digit. So let's look at some numbers first of all. I'm just making these up off the top of my head. Very uninventive here. This one has 1 as the first non-zero leading digit, because of course you can always throw as many zeros as you want in the front, and that doesn't mean anything. So you go to the first non-zero leading digit, this guy has 1. This guy has 2, this guy has 5. Benford says this: 1 is actually more common than other numbers as a leading first digit in many applications. Now your book has a full version of Benford's law, and Benford's law has been modified and then recalculated sort of over the years for different scenarios, but I've collected this and collapsed them down. So I said 1 has a 0.301 chance, so there's a 30% chance of the number 1. That leaves us with a little under 70% chance to split between the other rest of the numbers 2 through 9. So 1 is a very likely number to see. We expect to see it about 30% of the time. So now let's look at this example. Suppose we're auditing a firm. Well, we're getting ready to. It's time to decide, is this firm have legitimate numbers in its books, or are people stealing from the firm in some way? What you could do is, if it's a very large firm, maybe you don't want to pull all their data. So pick a random sample. Just pull 364 numbers from a large collection of financial transactions. This Benford calculation, it's kind of, I don't know when I want to say it's universally true. I'm not aware of any number theory results that say it must be this way, but this is the way it seems to work as a feature of when you have distributions of numbers and maybe even distributions of distributions. So if we have 364 that we pull out of our sample, and we find that 152 of them have a first digit that's non-zero, that's 1. So 152 have a non-zero digit of 1. At the alpha of 0.01 significance, and we'll talk about the consequences of that in a second, should we pay to have a full audit? Have we done something unusual? Is it time to call the police? Well, let's take a look once again. Remember our universal truths. H0 can be true, or H0 can be false. We can decide to not reject H0, or we could decide to reject H0. And that gave us our little grid. And as we looked at this, if H0 was true and we chose not to reject, then we made the correct call, so we're correct. And also, if we reject H0 and H0's false, that's also correct. But here, this was a type 1 error. This is what happens when we reject the null hypothesis, but it is in fact true. This is what happens when we give no treatment. Excuse me. Let me rephrase that. We have rejected H0, so we give a treatment, but there was no disease. This has a level of significance alpha, and that's where we choose to pick our alphas. Here we've been asked in the problem to pick an alpha of 0.01. This is also an error. It's a type 2 error. We have beta. And when we've got this, this is where we have no treatment. We do actually have a disease. In the case of our financial example, because remember this was for medical terms, in this case we choose to not have an audit, and my firm's books were actually healthy. No audit, no thieves. I think I before E. Here, we chose to reject the null hypothesis that nothing significant was happening. So here we called an audit, we paid for an audit. And since H0 was false in real life, there actually are thieves. Makes our firm very sad. But either way, here we've made correct judgment calls. So as we choose to pick certain levels of significance, let's rebrand these, not with treatments and diseases, but with what kind of decisions we're making. If we do not reject the null hypothesis, that means that we're saying nothing strange is going on, so we decide no audit. But there were actually thieves. And that's unfortunate. That's even worse than this one, I suppose, because we didn't even catch them. Over here, we've rejected the null hypothesis, so we've decided to do an audit. We paid for an audit. But the null hypothesis was true. There were no thieves. We just wasted money. So here, wasted money is the consequence. Here, free thieves is the consequence. Here, we've also lost money. Well, no, we haven't lost money. We paid for the audit, so we lost some money there, but hopefully we gained it back from the thieves. So who knows here. Either way, these two cases, we kind of made the correct call. This one's obviously the cheapest. In a perfect world, my advice to you is don't have thieves in your company. It's cheapest. But this is what we're looking at. We picked an alpha of 0.01. We picked an alpha of 0.01 probably because it costs a great deal of money to conduct a full audit. And also, it tends to make your employees not trust you all that much because you've started the whole system by not trusting them. Also, generally, firms have pretty strict, especially large ones, have pretty strict financial controls. So it's not like anyone can just walk into some money pot and take money. Usually it's complicated to steal money from a firm. At least that's the goal of any good financial side of your firm. I know, for example, at my college, I have to get about 3 signatures before I can request reimbursement for things if I go on a conference, since it's paid for by the college. Normally, I pay for it myself and then get reimbursed. So it's not like just anybody can go and take money even from the firm. I suppose I could try to rip into the walls and sell copper wire here on the weekend, but that would be tough. Usually it's difficult, you know, office supplies on eBay, and I should probably stop imagining how to steal from my firm. So you've got this idea that maybe it's usually somewhat difficult for this thing to happen, so we pick a low alpha so we don't accidentally trigger a full-scale audit, just because. Alright. But now we have to figure out what types of things to do. So we have to go ahead and design our 5-step process. Again, remember, words matter. If you're able to attach a word to something, when you look at a problem and say, should I make a decision, yes or no, I want you to instantly think hypothesis test, and as soon as you do that, I want you to think 5-step process. Step 1, we have to talk about the null and the alternative and the alpha. The problem's told us alpha is 0.01, so I'm going to go ahead and fill that in there. The null hypothesis is going to be that there's no significant difference. In this case, we don't have mu, we've got p. In this case, we're thinking that little p should equal 0.301. Now, if I go ahead and take my calculator and calculate this, I happen to know that p hat, so note over here, so this is maybe some of that initial scratch work calculation, p hat is equal to 152 over 364, which is approximately 152 divided by 364. I'm getting about 418. 0.418. This looks higher than 0.301. So I start to worry that we've got too many ones on the books. This means our alternative hypothesis is that p is actually bigger than what it should be. Therefore, we have a right-tailed test. Remember the discussion last time, right-tailed or two-tailed. Here, once again, we have 2 possibilities. We could go with a right-tailed, or we could go with a two-tailed. A left-tailed makes no sense this time. Last time, a right-tailed made no sense. Since this isn't life or death, since I might as well pick a single-tailed test because I usually find that easier to explain, particularly since I personally, if I imagine doing this myself, if someone hired me to do an analysis and say, is it time to do an audit, I'm probably talking to corporate decision makers who have very little, maybe, understanding of the mathematics behind this. I admit it is a much easier sell to say 0.418 is bigger than 0.301, so we went with a right-tailed test because it's bigger. Now that's a very maybe dumb reason overall to make any decisions, but the fact is that statistics is about taking mathematics and applying it to real life in a way that eventually you can write this English sentence that allows people to make a decision. So it's important that you're able to describe why you picked your alpha. That's why we wrote that little decision tree here and reworked what type 1 and type 2 errors were. Because if I pick an alpha of 0.01, well, one, I might simply look at, I don't know, some kind of financial journal and say, what do you guys usually do? And I'd say, we picked alpha of 0.01 because that's what we always do. Or that's what you guys did at your firm the last time you ran one of these audits. I would be asking those questions. But more importantly, even if not, I would look at them and say, look, do you trust your people? Did you try to hire criminals or did you mostly hire honest folk? And they say, well, I mostly hired honest folk. And then I'd say, do you know what an audit costs? And they're like, yes. And I'm like, do you really think that so much money is missing that it's time to hire one of the big 4 audit firms? And they probably say, well, I'm not aware of any money missing. We're just trying to check and see, how things are going. We're trying to nip any problem in the bud. And so I say, all right, so we really would rather not trigger an audit accidentally. Let's make this low. That would be my logic and description of why we're making these calls here. Okay, so consequently, the same way I would say, well, 0.418 is a little bit bigger than 0.301, so I decided to go with a right-tailed test. Next, it's time to calculate our test statistic. For our test statistic to make sense, this is a binomial situation. Either we have too many ones or we don't. And that's why I collapsed the Benford's law table down in this scenario. Either it's time to trigger an audit or it's not. And so as we're looking at this, well, do I have at least 5 wins and 5 losses? And wins are very strange, but here wins are being registered for us as having non-zero of 1. Definitely I have more than 5. In fact, I have 152 of them. That means that 364 minus 152 tells me how many times I didn't get a 1 in the first digit. I don't have to calculate that exact number to know it's bigger than 5. That means empirically, like we talked last time, we have a strong sense that the binomial distribution can be approximated by the normal distribution. We had at least 5 wins and 5 losses on the other side of us going on here. And that means we sort of checked off this double check thing that we have to always check before we're allowed to carry on. And it's now time to calculate our score. We're going to use normal distribution. P hat was calculated to be 152 over 64, over 364 rather, minus 0.301 divided by the square root of P, Q, and N. We don't know, excuse me, we do know P and Q, don't we? We got 0.301. And 1 minus 0.301. And also N, which was 364. So I can pop this into my calculator. Go ahead and reset that calculator. I probably have shown you how to reset your calculator, but it seems like a while since I did it. So if you've got a whole bunch of data in your calculator and you want to make sure you're not accidentally using old numbers, you hit the second button, you hit 0, it'll ask you to reset. If you hit the number 2, it'll say that all memory's been cleared. It's reset the calculator to its fresh state, so you don't have any more numbers hiding out in any of your lists. So maybe when you do some calculations, nothing bad happens. So on the top, I hit a fraction bar and another fraction bar, and I put 152 over 364 minus 0.301. Okay? Now I have a square root on the denominator, so I hit the second and square root button. And once I've got that, I put another fraction bar in there, and on the top I have 0.301. And then I'm going to use parentheses. I'm going to put a little times, times, and then open parentheses, so I'm going to add in my calculator times button. I don't know if our calculator does that times button or not. Some do, some don't. Who knows? Parens, and then I'm going to do 1 minus 0.301. I could have calculated that out, but it's just as easy to put parens in there. And then 364. and I'm getting a z-score of 4.849. I will make that a rough approximation. Remember, z-scores, we can only look up to 2 digits anyway, so 4.85 when I round it. So much for my calculator. This is my z-score. And if I'm looking at this as a normal distribution, what I'm saying is this. Somewhere we're thinking that we've got 0.301, and that's p, which is something of our average. We're looking at a right-tailed test, and we currently have 0.418. If we recalculate that, those were our raw p-values. If we look at this now in z-score terms, this is 0, and this now has a z-score of 4.85. That's a really, really large z-score. In fact, if you take a look at your chart, for most purposes, anytime we have a z-score bigger than 3.49, we're going to use 1 to approximate the area to the left. So I think that 1.000 is what's here on the left, and that means we've got 0 here on the right. This right area, since we're doing a right-tailed test, is my p-value. Step 4 is where we make a choice. Do not reject h0 or reject h0. Well, p is 0. 0 is in fact less than or equal to 0.01, which is the alpha we've decided to use. So this is p, and this is alpha. P is less than alpha. That means we're going to reject the null hypothesis. And now it's time to translate this into English, step 5, which I always kind of like to write up here because maybe this is part of the action item that I would give a client if we were doing this in real life. We've chosen to reject the null hypothesis. That means we've chosen to go with the alternative hypothesis. P is bigger than 0.301, so we would say there is statistical evidence that these financial logs are not behaving usually. Can I look that client in the eye and say, you've got a thief? No, I can't. I haven't proved anything. Even if I had somehow come up with, 0 is incredibly small, the chances of accidentally, randomly grabbing 364 numbers and having 152 of them, this is a lot higher than this. A lot higher. It's almost half. Granted, that's 30%, but this one's approaching 50%. The chance of having 50% roughly of all your data start off with 1s, that seems pretty unusual. I haven't proved it, but we found statistical support. It makes sense that we should look a little deeper. Things that I would say, well, there's statistical evidence that these financial laws are not behaving usually. Before we went all out and started to do a full audit, I would probably have these concerns that I would raise. Concern number 1, I would be curious, do we happen to know the last time there was an audit? Let's say there was an audit 10 years ago and that audit found nothing. I might suppose that the data from 10 years ago was pretty accurate in terms of no financial thievery, in which case I might go ahead and compare those numbers to that. Maybe this is a very strange firm that just so happens to have a lot of its financial entries have a leading digit of 1. Maybe this firm's the one weird one out of all of them. So I might look into that a little bit. Other things that I would of course look at is I would also recalculate before I go and tell the president of a company that you probably have a thief maybe. I would maybe recheck my calculations. But overall, there's statistical evidence to say that something weird's happening here. This is Benford's law, and you can use this in more things than just a firm's financial logs. Go around a store. Go around as your supermarket and look at the prices. We have an abnormal attraction as human beings, in some reason, to have a first leading digit of 1. Regardless of all the other numbers, we like to have the number 1. In fact, if you look at Benford's law and look at the full piece, you'll see that in general, the numbers at the beginning, we seem to prefer those more than ones at the end. Case in point, when was the last time you saw something sold for exactly $30? Not so much. When was the last time you saw something that was $29.99 or $29.95? Think of houses. Nobody says that a house is going to sell for $2,000. They'll say $199,999. They'll say under two. We seem to like to not see that next leading number being bigger freaks us out. I would say it's probably a human condition in our minds that maybe leads us to bin things. So if I see 30 and say $30, I know that's $30, but a simpler thing is, what if I also see the number 37? Maybe I also think of that as about $30. So on the scale between $30 and $39.99, maybe my brain's kind of automatically giving that a central weight of $35 roughly, and so it's better to write something as $29.99, because that way I'm thinking secretly to myself, well, that's roughly 25. You get some value there at the very high end of a range. People like to pull it down just a little bit. So anyway, this is Benford's law. This is very much used in accounting analysis. Now, of course, there probably are ways of getting around that. In fact, I can think of 3 if you're deciding to steal from people, and really I seem to be thinking about that a lot today, which probably means it's time for dinner. But look at this. Think about this. There's, of course, more advanced methods to do than just a Benford's law analysis before you decide to audit a firm, or even as part of a firm auditing thing. This is a bit of what's sometimes called forensic statistics. I find it hilarious, well, not hilarious, but I find it excruciatingly fascinating. I find it fascinating because it's very exquisite. I enjoy the mathematics of this kind of thing. It's a very cool way to take a lot of numbers and to get an analysis and come up with, I find, a very real-world sense of what's going on. You can do this with a lot of things, and not just Benford's law. Let's say that you're in a hospital and you think that maybe more morphine is being used than you have patients using morphine. You can do some statistical analyses to say, do we just happen to have a week where there's more patients being injured and so they need more morphine? Or do we have a morphine thief? You can do this with a lot of scenarios, and anyway, I find it very interesting to do this kind of crime type analysis. Maybe. It's not always crime. But anyway, you can do that. So that is binomial probability calculations. We've finally seen a right-tailed test. I think that we will continue on in this module talking about pair distributions. Remember, in the confidence intervals, we talked about this idea of independent versus dependent. And we said that for confidence intervals, we were only going to do independent. Now for this hypothesis testing, it's time for us to make that just a little bit more powerful. So I'm going to have a series of 2 videos that will both of them talk about pairwise comparisons, one where we're independent and one when we're dependent. And you're going to again see it's the same 5 steps. We're just going to have to change the way we calculate this test statistic. And of course we're going to have some different possibilities for each of those. So again, notice what you've seen. You've seen z-score, t-score, and then z-score with the binomial flavor. So now, as we do independent and dependent, be on the lookout and see, are you going to find for each of those categories, z-score, t-score, and binomial probability? Or will one of them only have one and one of them have the other? How will that work? So be thinking about that. All right, I think that starts to wrap up what I want to talk about today. I think this is getting us pretty close to finishing Chapter 8. We only have to talk about pairwise calculations. So be thinking of this. Fair warning, this is one of the most interesting. I told you I found this fascinating. Fascinating is usually code for me that it should probably show up on the final. I don't know that that means Benford's law is going to show up on the final, but it does mean that hypothesis testing absolutely will show up on the final. One of the most common mistakes I find people make is that you don't, when you're first learning this, it's hard. I'm not accusing you, I had this myself. As you first learn this is a lot of steps. And it seems it's too easy to get seduced by the fact that each one of these tests has some different calculations. So there's the z-score, the t-score, and so you spend so much time looking at the differences that you forget to take a step back and look at the whole picture. Really focus on the right side of the board and realize I've just been making teeny little erasures about right here. and accidentally here, but about right here for each one of these tests, which means Chapter 8 is actually an incredibly short chapter. As long as you understand binomial and t-score distributions, which as long as you understand Chapter 6 and central limit theorem, z-scores make a lot of sense. You're comparing a collection of terms in a sample to a population average, with variations, of course. So be thinking about that. Be thinking about how to make all of this make sense in your mind. And also, I think that I'm definitely working on ways to make Excel, some Excel videos. I have one, I think that's about ANOVA, but perhaps I should be making some more. Be looking for those, but until that happens, don't wait on me. You should be looking and thinking, how can I make Excel work? Because the more you can make Excel happen, the more I think you can kind of see all your data in real time. It's kind of hard when you plug numbers into your calculator to see how it's all fitting, but maybe if you calculate it in Excel, you can see where all the pieces come from, and that's a really good way to get your hands dirty. But until next time when we talk about pairwise testings, be safe, and I will see you in the future.